Scientists have discovered something unexplainable on the dark side of the moon. The lunar surface has always been a source of intrigue, with many countries attempting to land, but only a handful have succeeded. And now, a new discovery could hold the key to understanding why landing on the moon is so hard. Let's talk about this mysterious discovery and what it means for the future of lunar exploration. In 1966, the Soviet Union's Lunar 9 mission achieved a groundbreaking feat by becoming the first spacecraft ever to softly land on the moon's surface. Prior to this achievement, our attempts at lunar exploration involved hurling objects towards the moon, hoping they would hit the target and relay some data back to Earth. Surprisingly, the Soviets were pioneers in this endeavor as well. In 1959, their Lunar 2 spacecraft made history by becoming the first human-made object to impact the moon, marking a significant milestone in celestial exploration. Fast forward to August 2023, and Russia attempted another soft landing on the moon with Lunar 25. However, this mission ended in failure, leaving the spacecraft crashed on the lunar surface, creating yet another crater and adding to the growing collection of human debris on the moon. This setback raises questions about the apparent decline in lunar landing capabilities, especially in an era where technological advancements are expected to be substantial. This decline becomes even more puzzling when considering the efforts of other nations. Japan, known for its advanced technology and manufacturing, attempted a moon landing in 2023 through the company iSpace, but their mission also met with failure. Additionally, India, home to some of the brightest engineers globally, faced a similar fate with their Chandrayaan 2 mission a few years earlier. So, what's behind these challenges in lunar landings? Despite the technological prowess of these nations, successfully landing on the moon seems to remain an elusive goal. The question arises, why is it so difficult to achieve a soft landing on the moon despite our advancements in technology and knowledge? One crucial factor to consider in the challenge of lunar landings is the moon's peculiar and uneven gravitational force. Unlike Earth, where gravity pulls consistently towards the core regardless of your location, the moon's gravity is far from uniform. While gravity on Earth smoothly decreases as you ascend, the moon's gravitational force varies unpredictably across its surface. Over the years, scientists have observed these irregularities, discovering that some regions of the moon have a stronger gravitational force than others. This inconsistency creates a lumpy gravitational field around the moon's perimeter. Notably, these unexpectedly strong gravitational fields are often found over certain impact basins, hinting that the excess mass from large asteroid impacts might be concentrated beneath these basins, influencing the moon's gravitational pull. In 2019, scientists confirmed the presence of a peculiar mass beneath the moon's south pole. Although its exact nature remains a mystery, this excess mass is estimated to be equivalent to approximately 2 quadrillion tons. The presence of this mysterious mass beneath the South Pole Aitken Basin, a colossal oval-shaped impact crater on the far side of the moon, adds a fascinating layer of complexity to lunar exploration. This basin, measuring 2,000 kilometers wide and several kilometers deep, was formed around 4 billion years ago due to a massive celestial impact. By observing the moon, it's evident that it has endured significant impacts throughout its history, likely resulting in the deposition of these mass concentrations in various haphazard locations. These random mass concentrations create an erratic and unpredictable gravitational force on the moon. As a result, any spacecraft passing over one of these areas on its way to land on the moon would be affected by this uneven gravitational pull. This factor, among others, contributes to the considerable challenges faced in lunar landings. While it's not the sole reason, it certainly stands out as one of the more intriguing and intricate aspects to consider when planning missions to our celestial neighbor. When delving into the annals of history, one glaring fact emerges. Most attempts to land objects on the moon have ended in failure. This trend began in the late 1950s and early 1960s when the earliest efforts were made. Naturally, given the limitations of technology at the time, expectations were modest. Even as NASA advanced into its Surveyor program in 1966, a series of robotic moon landings paving the way for the Apollo missions, success remained elusive. Among the 7 Surveyor missions, one veered out of control mid-course, hurtling into a crash landing on the moon. Another mission lost radio contact with Earth merely 2 minutes before its intended landing, leaving the fate of the mission shrouded in uncertainty. However, the Apollo missions marked a significant turning point. Notably, there were no failures in the human landings on the moon during the Apollo era. This success can be attributed to a fundamental difference. Humans possess the ability to solve problems in the heat of the moment, a capability robots lacked then, and to some extent still do. This fact became glaringly apparent during the Apollo 11 mission. As the lunar module, named Eagle, separated from the main spacecraft, it immediately went off course. The computer guidance system was incapable of handling unexpected deviations. It merely followed pre-programmed calculations that would have led the crew to certain disaster. It was at this critical juncture that Neil Armstrong, with his piloting skills and quick thinking, made the decision to override the computer and rely on his instincts. ultimately averting a potential catastrophe. Appreciating the challenges faced by modern lunar missions adds another layer of complexity to the equation. In the early days of moon landings, simplicity ruled the approach. Lunar landers followed paths of least resistance, ensuring straightforward trajectories. For instance, the Soviet Lunar 2 impact in 1959 followed a ballistic trajectory, aiming directly at the moon's visible side, hitting dead center on the east-west axis and about 30 degrees north of the center. With more controlled landings like Apollo, landing sites were meticulously chosen on the moon's visible side, near the equator. This strategy allowed spacecraft to follow a relatively flat, two-dimensional path, launching from the Earth's equator region, traveling directly to the moon's equator region, and back. However, the paradigm shifted when the Chinese Chang'e 4 mission achieved a soft landing on the far side of the moon in 2019, breaking the established pattern. Recent lunar excursions, such as the failed attempts by iSpace and Lunar 25 landers, have targeted the moon's south pole. This region is crucial for future human exploration, because scientists believe its depths conceal vast reserves of water ice. Water essential for drinking also contains oxygen for breathing and hydrogen for fuel, critical resources for lunar missions. To access these resources, spacecraft must be inserted into a polar orbit around the moon, necessitating a more complex three-dimensional flight path. Landing at the moon's south pole is challenging but not impossible. India demonstrated this with its successful Chandrayaan 3 mission. Interestingly, India's accomplishment was partly due to learning from failure. Their Chandrayaan 2 mission, while not successful, provided invaluable lessons. Most would agree that the best way to improve at any endeavor is to attempt, fail, learn from mistakes, and apply those lessons to future endeavors. Sending robots to the moon remains an ongoing process, dependent on funding and determination. As long as there are sponsors willing to support these missions, scientists can continue launching robots into space, learning valuable lessons along the way. NASA's lunar endeavors in the 1960s serve as a prime example of this learning curve. Among the 9 Project Ranger missions attempting soft landings on the moon between 1961 and 1965, only the last 3 succeeded. This pattern of initial failures and subsequent successes continued with the Surveyor missions. Out of 7 attempts, 5 managed to touch down on the moon, indicating significant progress. The Apollo missions, the pinnacle of lunar exploration at that time, followed a similar trajectory. Out of the 6 missions that reached the moon without any failures en route, all 6 were executed flawlessly, marking a monumental achievement in human space exploration. This same trend is visible in the 21st century race to explore the moon's south pole. Despite the incredible advancements in computer technology, including transistors and microchips, failures still occur. However, these setbacks serve as stepping stones towards success. The process underscores a fundamental principle. Sometimes one must stumble before finding the path to triumph. With the race to the moon heating up once more, it will be interesting to see if NASA can leverage its prior experience and be the first to return to the moon, or if new competitors like China will come out on top this time. What do you think? Can NASA and SpaceX win this new era of the lunar race? Please let us know in the comments below.